All right, here's our video on energy in space. So we're looking at when we don't have something that is, right, we normally look at things on the surface of the Earth, but if it's not on the surface of the Earth, then our energy changes a little bit. So when we have things in space, let's say we have a star, and this star has around it a planet, like, a lot of stars do. Planets, um, when we think about a planet orbiting around a star, we often think about it in terms of this fairly circular pathway. And that's just how we usually think about it, but that's not the case. Planets don't go around stars in circles. Planets go around stars in what we call ellipses. So sometimes the planet is closer to the star than other times, and sometimes it's further away than others. This was a hypothesis of why Earth has seasons. Just first of all, as an aside, we the one of the hypotheses said that when Earth is closer to the sun, that must be when it's hotter. So when it's summer, but because the northern and southern hemispheres have different seasons at different times, we know that that can't be the case. Just as an aside, actually, fun fact: northern hemisphere winter. So our winter is when the Earth is closest, and our summer is when the Earth is furthest from the sun. That's just as a northern hemisphere. Southern hemisphere gets the opposite. Anyway, back to energy and space. So, right, we start with our planet way over here. Let's say we'll start at the red dot. As we move in toward the green dot over there, make this pen a little bigger. So as we move from the red dot to the green dot, our planet is getting closer to the sun. Well, we've looked at, to make an analogy to the Earth, right? The surface of the Earth, if I have a box there and then I lower the box down, I am decreasing my gravitational potential energy, decreasing U sub G because the box is getting closer toward the thing that's exerting gravity on it. The same thing is true here. So this red planet, from there to the green, it's getting closer. So closer, which means it is decreasing its gravitational potential energy. And then the same thing is once again true from that green position to the blue position. It's again getting even closer as it's moving around that ellipse, so it is decreasing gravitational potential energy. Well, if something decreases gravitational potential energy, right, energy doesn't just disappear, it must increase something else in terms of energy, and it does. When planets move around stars, the closer they get, right, when we decrease that gravitational potential energy, it turns into kinetic energy. So as we get closer, we increase kinetic energy. We increase kinetic energy. And that makes the planet speed up. So over here, where the planet is the closest, when it's the closest to the sun, that means it is moving the fastest. And then over here, when it's the farthest away, that means our planet is moving the slowest. Right? Because further away it is, the more gravitational potential it has. The closer it is, the more kinetic it has. And then we could see this happening again if we add like another dot, but it will just happen in reverse in that case. So as now we're getting farther. So we will increase gravitational potential energy. But when we turn some of that energy into gravitational potential, that means we have to decrease the kinetic energy. And I'll just get rid of this because we're done with that analogy to Earth's surface. Then it remains the same as we get even further away. So we get farther. So U sub G is increasing and kinetic energy is then decreasing to maintain initial energy equals final energy. Right? We do officially have, oh, didn't get it all. We do officially have work in this expression here, plus or minus work. But are there any outside forces acting besides just the gravity between the planet and the sun? No, there's not. So we get that our initial energy must equal our final energy because there are no outside forces. Okay, so there's our general principle as we have elliptical orbits. Elliptical orbits. And that is something that we will come back to when we look at another one of our units, circular motion, elliptical orbits, which means that planets get closer and further from their sun. That's also the same with a moon orbiting around a planet. Anything that orbits something else, it will happen in an elliptical orbit. So it'll get closer versus further. Okay, so there's one of our general principles there. The other thing to point out is this equation here. Okay, so we have our gravitational potential energy in space. It looks very similar to our force equation in for objects exerting the force of gravity in space. It looks very similar, and right because we have this work as it's the change in energy, but we can calculate it through force and displacement, whatever force is parallel to the displacement. So, what if we have the force of gravity? So I'm going to take this as the change in energy will be the force of gravity times however far something moves. Well, the force of gravity is gm over r squared. I should say this as an aside. You do not have to know this derivation. I'm just showing you where this comes from, but you don't have to know it. So our change in energy for something happening in space, gmm over r squared. But if we're also looking at how far away something is, right, how far away something is from the planet, that's going to be our displacement to come up with the change in energy. So that will be the displacement. However, because that's the displacement, we can say that it's equal to r. Okay, so then what that does for us is that r goes away with the squared. So our change in energy is gm1 m2 over r. Okay, so that's kind of how we derive this equation here. And you might now be saying, but Mr. P, what about that negative sign out front? And I'm so glad you asked. All right, as I have this sun with the planet, as the planet gets closer, that means r is decreasing. But we also know that that means gravitational potential energy has to decrease. Let's take a look at our equation over here. If r is decreasing, that means that our denominator is decreasing, which would give us a bigger number. So that would make delta E get bigger. So we would have a larger energy as we got closer. That can't be the case. So what we do is we stick this negative sign in front, which means that as our radius decreases, this numerical value gets larger, but that just means it becomes more negative. So our gravitational potential energy would decrease. Again, this is something that you don't have to know the derivation of, but it's just good to know, good to note, and to be able to see. So our gravitational potential energy in space, we can calculate that by taking the negative of gmm over r. That's for any two objects interacting in space. So yes, it is a negative, but really, because energy, all we look at is how does some energy transform into other energy. So that won't affect what we come up with as far as energy goes. Okay, let's take a look at our class problems here. So energy in space. So we show here a satellite is shown at point A, orbiting the Earth in the clockwise direction. So it's orbiting in that way. The dashed line represents a circular orbit. And remember, things don't orbit circularly, they orbit elliptically. So the dashed line represents a circular orbit at a distance of lowercase d above the Earth's surface. And the solid line represents the path of the satellite. So it's traveling in an ellipse. Okay. Part A asks us, how does the total energy of the satellite compare between points A and point B? Well, all right, total energy, E naught plus or minus work equals E final, but is our energy changing? Is anything actively exerting work onto this satellite? It's not. The only thing that's happening is it's moving further away, so it's changing its gravitational potential energy. So it total energy remains the same. Okay, how does gravitational potential energy of the satellite compare between A and B? Well, it's moving further away from the Earth's surface. So if we're getting further away, gravitational potential energy has to increase, just like lifting a box up over the surface of the Earth. Okay, then, as a result of parts A and B combined, how would kinetic energy of the satellite compare from point A to point B? So it's currently at point B. How does it change? Well, if our gravitational potential is increasing, right? So we have E naught equals E final. It starts with a lot of kinetic, and I should say, because it's at its closest point, a lot of kinetic, little bit of gravitational potential. And then we get a lot of gravitational potential. So what has to happen to its kinetic energy at point B? It has to be small, just a little bit of kinetic. So our kinetic energy will decrease in order to conserve the energy. All right, right. The equation for the total energy E of the satellite at point B in terms of the types of energy that exist at that location, then substitute in the equations for those types of energy. Okay, we're looking at satellite at point B. Satellite at point B. Okay, well, the energy at point B, at point B, because it's far away, it has gravitational potential energy, and it's still moving. Otherwise, if it wasn't moving, it would just fall straight down to the surface of the Earth. So it has gravitational potential and kinetic. Okay, then substitute in equations. So the energy at B, gravitational potential energy, this is for something in space, negative capital G, mass 1, mass 2 over r squared. Remember, this capital G is that constant, same constant that's in the equation for the force of gravity in space. And then plus kinetic energy, 1 half mv squared. Okay, so there's the types of energy, and we substituted in for what we could. All right, part E, the satellite is moving at 3,000 meters per second at point B. If point B is 12,000 kilometers, but we don't like kilometers, so we need to change that to be 12 million meters. All right, we have 1,000 meters in every kilometer. 12 million meters above the surface of the Earth, and point A is 2,500 kilometers, so 2.5 million meters above Earth's surface. How fast is the satellite moving at point A? We'll use the concepts that we use to answer everything above, not just 1A, but everything above. Okay, so we can say what we did up here, right? Because there's no work happening, so we know that the energy at point A has to equal the energy at point B. Energy at A, well, there's a lot of kinetic because it's close, and a little gravitational potential because it's close, right? Because it's moving faster. It has to move faster when it's closer to maintain the energy. Will equal, and then there's when it's far, it's not moving fast, but it's further away, so we have more gravitational potential energy. I wrote this as the larger the letter, the more energy it has, which that's just to dramatize this for you in this question. You're more than welcome to do that in future questions, but I won't. I never grade for that. Okay, so we have, and I should say these are all at point A, these are all at point B. Okay, 1/2 mass, and this is, right, kinetic energy of the satellite is mass of the satellite, and whatever the velocity is at point A squared plus, and then that negative G m1, m2. Well, this is the Earth exerting a force on the satellite over r. Remember, it's not over r squared, it's just over r. And then 1/2 mass satellite, I should say RA, sorry, radius of A. 1/2 mass satellite times the velocity at B squared plus, and then the gravitational potential is negative G mass of what's creating the gravity times the mass of what's feeling the gravity over the radius of where it is now, B. Okay. Let's take just a moment and say what is, or is there anything in every term that we can get rid of? And there is the mass of the satellite we can get rid of. Okay. Now, let's see. Do I give you any more information about the Earth? I do not. Okay. I would have to probably give you more information about the Earth. So we'll go through that, and I'll write down that information. 1/2 velocity at a squared minus G mass of Earth over RA squared is equal to 1/2 velocity at B squared minus, oh, I'm sorry, there should not be a squared on that radius from A, minus G mass of Earth over radius at B. Okay, we can start to plug some stuff in now. But before we do that, I have to give you some information about the Earth. The Earth, and I'm just going to Google this to make sure I'm giving you the right numbers. Mass of the Earth in kilograms. Yes, okay, so the mass of the Earth, and I'll write these up here just so they're out of the way a little bit more. Mass of the Earth is 6 times 10 to the 24th kilograms. And then I also have to give you the radius of the Earth. The radius of the Earth in meters is 6.4 times 10 to the 6th meters. Okay. Now, why did I have to give you that? Well, I tell you that point B is 12,000 kilometers above Earth's surface. Point A is 2,500 kilometers above Earth's surface. But remember, all of these gravitational equations, G, M1, M2, in this case it's over R, this radius must be equal to, sorry, I forgot the negative sign. This radius must be equal to the distance from the center of one object to the center of the other object. So from there to there, and that's the radius, or from there to there. So I can't just give you the distance above Earth's surface. I have to give you the radius as well so we can find the total distance. Which just means whatever this distance is, we just add the radius of the Earth to it, and then we'll get our total distance. Okay, so let's take a look at that. 1/2 velocity at point A. That's what we're looking for. How fast is the satellite moving at point A? So 1/2 velocity at A squared minus, and then G is 6.67 times 10 to the minus 11. Mass of the Earth is 6 times 10 to the 24th kilograms. over. And then the radius of A, right, that has to be the radius of the Earth plus, I guess I don't need the meters in there, plus whatever the distance above Earth's surface is at point A. So plus 2.5 million. So 2.5 times 10 to the sixth. 2.5 times 10 to the sixth meters. So there's our R on the bottom, radius of A. Okay, equals 1/2 velocity of B. I tell you that it is moving at 3,000 meters per second at point B. 3,000 squared minus, and then G is 6.67 times 10 to the minus 11. Mass of the Earth is 6 times 10 to the 24 divided by, okay, and then R added for radius of B, well, surface of the, or the radius of the Earth, 6.4 times 10 to the 6th meters, and distance above Earth's surface is 12 million, so 12 times 10 to the 6th, so we add those together. Okay, let's pull out our calculator now. So 1/2 velocity at point A squared minus, all right, 6.67 times 10 to the minus 11 times 6 times 10 to the 24 divided by, and then use parentheses because we want to divide by the sum of these two numbers, 6.4 E6 plus 2.5 E6, close parentheses. All right, so that first term here, I get 1.56 times 10 to the 4, 5, 6, 7, 8, 10 to the 8th power. Okay, then over here, 1/2 times 3,000 squared, I get 4.5 times 10 to the 6th minus, and then this is similar to the other one that we just did, but instead of 2.5 times 10 to the 6th in the bottom, it's just 12 times 10 to the 6th in the bottom. So I get 3.3 times 10 to the 2, 3, 4, 5, 6, 7th over on that side. Okay, so I will take 4.5 times 10 to the 6th minus 3.3 times 10 to the 7th, add 1.56 times 10 to the 8th. So I'll get 1/2 velocity at A squared is equal to 1.275 times 10 to the something here, 8. All right. And if we solve this for the velocity at point A, times 2, square root that number, I get right around 16,000 meters per second. Okay, 16,000 meters per second. So that's moving significantly faster than it was at point B, which does make sense, right? Because it is a lot closer than it was at point B, so it's moving a good chunk faster. And it's on a v squared function, so the velocity will increase pretty quickly compared to the distance. All right, so there's our first question there. Moving on to the second and final page. All right, so it's still on the same question for these first couple, at least. For which one of the above graphs best represents the gravitational potential energy from the Earth at the location of the satellite as it orbits? Briefly explain your reasoning. Just as an aside, this question is straight from AP. This is one that came from an AP test. It was from an AP test that was given nationally. Okay, which one of these graphs represents the gravitational potential energy? Well, at A, right, if there's the Earth, A is there and B is over here. So A, it has to have more than B. So let's see, this one, A and B are equal. A has more than B, A has less than B. So it has to be graph 2 because UG at point A must be greater than gravitational potential energy at point B. Oh, I'm sorry, less than. Nope. Okay, not graph 2. Let's back up for a moment. It is graph 3 because UGA less must be less than gravitational potential energy at point B. Thank you for bearing with me. Sorry. Because radius of B is greater than radius of A. By the way, if you ever put something like that in, um, if you ever do something like that in your AP test, just to write it like this, they totally accept it and they're totally fine with that. Okay. Now, the total mechanical energy. Well, total mechanical energy, what does that mean? That means all of it together. Well, there's no work, so we know that energy must be constant throughout. So this would be then graph 1 would be the total mechanical energy because no work is done. Maybe it'll let me write. Here we go. No work is done. So energy initial must equal, or I should say energy at A must equal energy at point B. Okay, which of the graphs best represents the strength of the gravitational field? Here's something that they really like is they love talking about fields. Essentially, a field is just how strong is the acceleration. And we know that the closer we get, the greater the force, which means the greater the acceleration. So the further we get, the less the force, the smaller the acceleration. When it says gravitational field, that means acceleration, is what that means. So for gravitational field, we want something to say when it's far away, it's smaller. When it's closer, it's bigger. Remember, point A is closer than point B. So we want this to be point A is greater and that would be graph 2. So this one is graph 2 because radius of A is less than radius of B. So that means that the field at A must be greater than the field at B. If it's closer, it has to have a bigger field for gravity or a stronger field because there's more acceleration. Okay, there's that question. Then we'll just look down over here. Second question. Okay, a rocket is continuously firing its engines as it accelerates away from Earth. For the first kilometer, the mass of the fuel ejected is small compared to the mass of the rocket. All that means is that we don't have to consider the fact that it's losing mass because that amount of mass is so small compared to the rest of the rocket. For this distance, indicate the changes, if any, to the kinetic energy of the rocket, the gravitational potential energy of the Earth rocket system, and the mechanical energy of the Earth rocket system. So the kinetic energy, let's see, it accelerates away from Earth, so kinetic energy will increase. Okay, and all we really have to say is that it's accelerating. Next up, it says gravitational potential energy. Well, it's getting further away, so that increases. Further from Earth. And if both of those types of energy are increasing, that can only mean one thing for our total energy, increasing. Because the energy is kinetic energy plus the gravitational potential energy. If both increase, total energy must also. And that's really all you'd have to write. This one is, again, the problem and the setup is taken from AP. I tweaked how I asked the questions, but it's an AP style question. Is this one? All right, there's our brief introduction on energy in space. We will go over this more as the year goes on. If you have any questions, please do let me know. Otherwise, I will see you next time.